But find the Cartesian equation for each curve. So what curves do they trace out? Well, you have to remember that what you're essentially trying to do is turn it into a Cartesian equation that you recognize. There are certain Cartesian equations that when you had never seen them before, you're like, that makes no sense to me. But now when you see them, they make automatic sense. Oh, that's an ellipse. That's a circle. So you're trying to put that into a form that you can automatically recognize. You need to remember basic manipulations. One thing you might try to have done first is square both sides immediately. Why is squaring both sides immediately something you might not want to do on this one? James?
It's very, very crazy.
It gets crazy really quickly because you get 2 plus cosine times 2 plus cosine. You get 4 plus 4 cosine plus cosine squared. It gets nasty, right? What should I do first before I square? James?
Isolate cosine t.
Yeah, if you just go x minus... Oh, look at this. We love this because when we have this, what happens when we square these things?
It's going to be a nice one.
It's much nicer. It's much, much nicer. And you end up with something that's recognizable. Because when you add these two together, what does that press together into? X minus 2 squared plus y minus 2 squared is equal to 1. It is a unit circle centered at what? 2, 2. That's a unit circle centered at 2, 2. Done. There are simple substitutions that you have to remember. Simple substitutions that you have to remember. The core identity we work with over and over again is sine squared plus cosine squared is 1. So basically you force that to happen and everything else is along for the ride. You force that to happen and everything else is along for the ride. That's the story of how many of these other ones go. Like creating that ellipse that was like 3 by 7 or something, right? You just have to find the right coefficients for sine and cosine that forces like x squared over 9 and y squared over 47, I think. 49. Yeah, something like that. Okay, who to do this question? Well, yeah, the equation of ellipse is x squared over something plus y squared over something else equals 1. What makes it an ellipse is that a and b are different values. If a and b are the same value, it's a circle, right? So you have to find, okay, so first of all, you have to figure out what your target is. And what's your target audience here? 9 and what?
47.
9 and 49. Because when y is 0, what should x be? Plus or minus 3. Well, that's true. When x is 0, what does y get to be? Plus or minus 7. And that's exactly what we want. So this is our target right here. And we're starting with cosine t and maybe y is sine t. You can add coefficients to the front of these functions that force these coefficients to generate. So what I recommend you do is, well, first of all, when you practice these out, you'll be able to immediately identify what the coefficients need to be. You have a strong idea. It's going to be something involving a 3 maybe. It's something involving a 7. So what I recommend you do is just literally pick one, go with it, and you'll either have it right or be so close to having it right that it means, oh, I just need to flip it over. Oh, I just need to make it negative. So a lot of you might have started with, I don't know, some of you might have started with x equals, some people are like, oh, okay, 1/3 cosine t. And y is equal to 1/7. Now this seems like maybe a good place to start because when you square it, what do you end up with? X squared is equal to 1/9 cosine squared t, and y is equal to 1/49 sine squared t. Oh, okay, but we don't really know how to, those coefficients mess it up, so you end up with 9x squared is equal to cosine squared t, not plus, and then you end up with 49y squared, oh, this is squared right there, equals sine squared t. Now, can you add the right-hand side? Oh, you could, but what's the problem? They're not where they should be, right? They're up above as opposed to below. So, oh, we didn't do the proper work, but did we almost do the proper work? This tells us that we need it to be x is equal to 3 cosine t, and y is equal to, but there's still one thing that's wrong.
It's not right starting.
It's not the right starting point. At time equals 0, this thing is at what point? 3, 0. Where should it be?
0, 3, negative.
It should be negative 3, 0. I think that's what the problem says.
Yeah.
Starts at negative 3, 0, right? So what can you do structurally? Yeah.
You just add t, add pi to both t's.
You could. That's a great way to do it, actually. I like that. There's an easier way to do it, though. That's true. No, that's fine. That's totally correct. What's another way to do it? Just make it negative 3 cosine t. Henry, I really like that method. I will give you your gold star for today because that hasn't come up yet. You absolutely could just rotate it around, right? You could change the index, or you could just take the point and move it.
But
Either way is fine. Hold on, Jesse, where?
How is
Instead of making it negative, he said x equals 3 cosine t plus pi, and y equals 7 sine of t plus pi. Plug in 0 into this.
Oh, I get that because you're just
He just moved it over, right? He incremented, like, at time equals 0, it's cosine pi. What's cosine pi? Negative 1. What's sine of pi? 0. So this stays 0, and this just rotates it 180 degrees around. It's another way to do it. I like that. That's cool. Totally valid. Again, though, how many different ways can you write the same parametric equation? A ton of different ways. Look at this. It's a little different. Why, Henry?
Because one of them is squared and one of them is not.
True, but what else is different about this? You have.
And then you have and they're both cosine.
Yes. Let's focus on that. We don't really like that, right?
I just came up with this.
What is cosine squared? Not theta. Why am I writing? Oh, that's okay. Is that true?
Yeah, but I have another.
Hold on. I understand. There's many different ways. There's a lot of different ways here. I'm just doing it. So what does this mean? It means that y minus 1 is equal to negative sine squared. Correct. So you also know that you could isolate that a little bit, and you could say it's 1 minus y is equal to sine squared t. Right. Over here, what do you have? X minus 2 is equal to cosine t. So x minus 2 squared is equal to, what's that equal to? Cosine squared t. You could add these together, and what do you end up with? X minus 2 squared plus 1 minus y equals what? 1. What cancels on both sides? 1 cancels, and you end up with x minus 2 squared is equal to y. So this is actually just a parabola. Are there many other paths you can take? Yes, there are many other paths. We can't do them all. There's a direct substitution you can make here. Like, look, I know, look, cosine is equal to x minus 2. So plug it in there, and you're done, okay? There's lots of different methods. It's the same thing. There's the same, but just remember, you might not get traction on the shortest method to begin with. This is awesome. This works fine. Totally works fine. There's lots of different ways. But always remember the substitution. There was one we worked on today, I think, which was easy substitution. Was it U-ray? That really easy one? Which one was that? Remember which number it was?
27.
On 27. 27 is like, oh man, you have to move it over and square it, and then everything seems to go away and something weird happens. Like 27. Take a look at this. You're like, man, I'm not sure what I need to do because there's 2 cosines. We love squared, so we want to keep on using that same tool, right? But like, look at this. From this one right here, what does cosine t equal? X minus 2. So then you take this, and where do you put it? Right there. So y is equal to 2 minus x minus 2. So y is equal to? Done. So we're sitting around like squaring it and trying to find trig. It's just a substitution, and then you're done. You're like, oh, yay. Okay. Put everything away except the pencil. You should be well familiar with by now. The slope of a curve, if for dy dx is going to be dy dt over dx dt. So how do we feel about the truth of that statement right there?
Very, very true.
Second derivative. Can someone explain to me what does that say? The d something y dx something. What is this? Can someone tell me what this is right here? What is it, Ray? The second derivative, right? And what does this tell you have to do to compute the second derivative? Given x in terms of t and given y in terms of t, what does this tell you need to do? So different. So you have dy dx, and what do you do to dy dx?
Divided by dx dt.
Not divide it. You differentiate dy dx with respect to t, and then divide it by dx dt. Do you know where this comes from? It does come from the chain rule. Exactly. It does come from the chain rule. Absolutely. Another way to think about it, the way it helps me, is you see this right here, dy dx, and you have dy dt over dx dt. If you instead have inside of y, dy dx, what happens when you plug it in? Oh, look, you end up forming this directly.
Yeah.
If y becomes dy dx, you immediately go from here to there. You need to make sure you have these down cold, okay? You have them down cold. Yes, James. Oh, you're agreeing with that? Yeah. Go ahead. I wasn't specific.
2 plus e.
2 plus e to the t. Exactly. What's y prime t equal to?
Well, that's 3.
3. So what is the velocity vector at time t? 2 plus
2 plus e to t.
Comma.
Oh, yeah, sorry, 3.
Comma 3.
Yeah.
Exactly. Right. That right there is the velocity vector right there. One thing that's nice about a parametric form is you can easily get the vector equation for the particle at any given moment. If you guys were to, in physics class, then write this, what does this mean? What does that mean? The bars around it. The magnitude. Close. It's not the absolute, it's the magnitude. How do you find the magnitude of a vector?
Well, the speed.
It is the speed, exactly. The way you find it, oh, the magnitude is going to be the first component. Oh, have we seen this already? Yeah. That is the speed. The magnitude of the velocity vector is the speed. So I just wanted to make sure we mentioned it briefly, and we did this one out before, but the idea is one advantage of having the parametric form is it very easily gives you the horizontal rate of change and the vertical rate of change, which can be very, very useful to have. Here's the new aspect, the new little piece here. What is this right here? That f prime of x is equal to delta what? Delta y over? So what does delta y equal? Delta y is going to be equal to delta x f prime of x. So that's where this comes from right here. If you want to find the distance between these 2 points, base squared plus height squared equals the hypotenuse squared, Pythagorean theorem. But if you want the distance, what you take the square root to isolate that distance. What did they do with this delta x? Is that delta x inside here? No. If you were to pop this back in, what would it become?
Delta x.
Delta x squared and delta x squared right there, which is what you get if you square this in this. The diagrams tend to simplify things kind of a little flippantly, and it's hard to follow sometimes. But the idea is, if you want to find the distance from here to here, how do you do that? That's going to be delta x squared plus f prime of x delta x squared square rooted. What can you factor out of each of these terms? The delta x. And what are you left with if you factor out the delta x out of this? 1. This goes to this.
So that's just Pythagorean theorem.
It's just an application of the Pythagorean theorem. That's it. Why is this really useful? It's really useful because now we can actually do questions